Welcome to another video explaining the universe using the particle model. Well, today's video is part 2 of the photoelectric effect. I have explained the photoelectric part 1 the last time. This is all part of a series that I started on the diode. And I did the basic diode itself and then the light emitting diode. And before I got to the photodiode, I decided to interject the photoelectric part 1. And this is part 2. So if you haven't watched them, by means go ahead and do so. The part 1 was all about varying the intensity while the frequency was at a high frequency. And they're using calcium as a material. You can see that the intensity at this point is very high. This is intensity, it's high. And this is the vertical is a current. They use a current meter to measure it. They have the battery sitting there at 0 volts. And they're just showing that, yes, the intensity of this light increases the number of emitted electrons, and the intensity itself is based on the number of photons being generated. A higher intensity, more photons generate, more electrons. Well, this is another chart I showed, which I used just to show the basic function of light hitting the material, and red light not emitting any electrons, while green and violet both generate. Well, I decided to check the math, and I chose the green light to do so. So here's the math. You start with the energy of the green photon using the equation they have. Frequency is actually speed over a wavelength. Planck's constant in terms of electron volt seconds is 4.1 times 10 to the minus 15. Speed of light, 3 times 10 to the 8th. And the wavelength of the green light is 550 nanometers, e to the 9th mean nanometers. And when you calculate, you get 2.25 electron volts, just like the chart said. So then I move on using the 2.25 and assuming that I can put that in for the energy of the electron, because the energy is conserved. Energy in equals energy out, so I can use this value here, 2.25. When you rearrange this and solve for V, you get the equation, which is the square root of all this. And hence I get this number, 8.89 times 10 to the 5th meters per second, not 2.96. And I looked at this several times. I must be making a mistake somewhere. On the other hand, I reverse the math and I get the same problem. In this case, I start with the velocity of the electron. I know what the mass of the electron is in kilograms. Of course, you know my opinion is that you can't, in the particle model, you can't state the mass of the electron in kilograms. And nonetheless, that's what they do, and you can calculate that. The energy is 3.99 times 10 to the minus joules, and you convert that to electron volts, and you don't get to 2.25, you get 0.249. Person who did the graphic made a mistake. Unless I'm making one, if someone out there knows what I did wrong, please let me know. Well, the second experiment in this video, this is the video I've been using, talks about a stopping voltage. And this is a general term used by people talking about the photoelectric effect in this particular experiment. What's done is, by reversing the battery, the electrons generated by the photoelectric effect, they affect the flow, and they say the electrons can be stopped by the battery. So the light is shining. In this case, you have a high frequency again to kind of guarantee that you've got a flow You have medium, average intensity, but now the battery is turned around and the battery has, they say, minus 3.2 volts because the battery is reversed. Their explanation is that this negative end charges this plate negatively, and as the light hits the plate, emits electrons, they're repelled by this charge. So the higher and higher you make this, you get to the point where none of these are emitted because of the force repelling them. And they know when that happens because the current meter will say 0 when you first start, and the intensity is low, or the voltage is 0. Excuse me. When the voltage is 0, you get a free flow this way, and they're flowing, in my understanding, but that's not the way they say it works. This is the one. This is the particle model explanation, and I claim the particles do not stop. Do not stop and hang in midair, being pushed back equally. Has this velocity here and being pushed back. What happens is represents the particle stream of lights, a peak, a valley, and so on, hitting these peaks hitting the atoms, the G1 orbitals hard enough, they get released as G1 and they flow this way. There is a G1 net G2 force field in this direction caused by the fact that this plate is losing G1s. This one may be gaining or may not be gaining, but that difference causes these particles to move this way, and they continue to move around the circuit. The particle model, when this is reversed, this is generating electrons, and it's sending electrons around in this way. And you adjust this voltage until current reaches 0. So what really happens is that the current going this way and the G1s going that way cancel, because when they're equal, the meter reads 0. That's essentially the basic explanation. However, I'm going to point out shortly that it's in the particle model, the value of B and the value of C are the same, and even though there's lots of them flowing through here. Okay, so the electrons don't stop. They just don't hang there and eventually stop lighting. But now let's talk about the effect of the battery and the tube. Suppose there are no G1s entering the tube. So the photoelectric tube uses light to add G1s to the number entering. And that's what I was saying here. They know that when there's no light, there's no electrons. Set up this way. You turn the intensity off. When you add the light, they're adding. These electrons are coming off of this plate going. They're adding. Whatever is going around, no matter how many are entering. If there were no entering, it's adding. If there was some entering, it's still adding. This is adding. Suppose there are no G1s entering the battery. So the battery uses a chemical reaction to add G1s. Now, back when I first applied the particle model to a circuit, and I realized that as the G1 particle went through a resistor, they hit and scattered, and hence we lost G1s. And I noted that, wow, there's a correlation, one-to-one type correlation of lost voltage and lost G1s. When it wasn't almost immediately I went around the circuit to the battery and said, wow, if it's going to be balanced and stable, battery has to add. The battery uses a chemical action to add. That's the first time that I ever heard that or thought that. My whole point is here that back when they were doing the photoelectric effect, they knew that the photoelectric tube was adding G1s based on the light being hitting the plate. They knew that, didn't make the correlation, didn't occur to them. Probably wouldn't have occurred to me had I been the one doing that back in time. Okay, so I analyzed this to try to determine how many G1 particles are really being involved here. And there's a theorem you learn in college or whenever you study circuits about, it's called the Superposition Theorem, which says if you have a circuit that has two sources, source 1, source 2, this has an internal series resistance, and this one sets up current this way, although some of them go that way. And this source causes current flow this way, but some of those go this way. What you can do is, in this first case, is you eliminate this and just short it out, and then you do the calculation. And in that case, you got current flowing this way, and it splits here, down there, and there. By the way, these are the parallel resistors. And that current knows which way to go. I explained that in the parallel resistor video, that it's decided right here at this connection point. So you can calculate this. Then the second one is you make this 0. They leave the internal resistance of this source here, and then they do the same thing. And you get current flow this way, down here, and it splits and goes into these two resistors. What you can do with the superposition theorem is that I1 prime and I1 double prime add up to make this. I2 prime and I2 double prime add up to get this one, and so on. It's called the superposition theorem. And so what I did was I did a spreadsheet where I assumed, typically that I do, I don't know the real value here. I assumed 0.1 volts per G1. I assumed the percent loss was 1 out of 1,000 per ohm. And I assumed, of course, this is a case where what they're using is 3.2 volts to stop the electrons, which I say they're not doing. And the result is that there are 63,000, almost 64,000 on each side of the meter. And there's the spreadsheet, and I split it. Here I'm using the photon, the light source, and no battery. Here I'm using battery and no light source, and I calculate how many are at C here and C there, and how many are at B here and B there, and I add them together, and they both come up 63,000. A lot of G1s flowing through there. Okay, the last test that they do is to show how energy varies with frequency. In this case, they set the intensity at medium, and they've got this reversed as if they're going to do a stopping, and you can see that they're, and so what they do then is they vary the frequency. They start at high frequency. High frequency is over here, so they start up here, and they plot energy versus the frequency, apparently implying that this experiment's what's doing that. They imply that, and they move the frequency up and up and up, and it goes all the way down to the point here where it hits a crossover, a 0 point, zero energy, and where there are none. Here's just before they're totally stopped at 3.2. So they're plotting, in this case, it's the same test as before, but now they're plotting it versus frequency instead of intensity. And from this, they do something else. Here, by the way, is the copper. This is different. The previous plate was calcium. Now it's copper, and it has a curve, and it has a different breakpoint. The other one was very close to this dot. This cutoff point, excuse me, is higher. So they have a cutter, but it turns out the slope is the same, and that slope always being the same for different materials ends up being Planck's constant. But be careful. I'm being duped and you're being duped here. Where did they get the energy? Where did they calculate that from? They are calculating the energy from HF. That's where they're getting it. So they're starting with the equation, this, and they're explaining all this, and then they do this, and it's classic circular logic. This is not an independent calculation of energy. If it were, then yes, and these curves were all parallel with the same slope, then it would be right. But as far as I can see, the video never indicates that there's an independent calculation of the energy of the electron or the energy of the light. It isn't the clear explanation. So I had to find out what was the right explanation. So I looked up Planck's constant. At the end of the 19th century, 1890s, physicists were unable to explain the observed spectrum of black body radiation. Now that's different, which is still considered to have been accurately measured, but it diverged significantly at higher frequencies. The curve starts going up, was supposed to go up, but the measured values then come down, whereas classically it should continue up. At higher frequencies, it didn't make sense, as predicted by existing theories. Well, in 1900, 5 years before Einstein did his paper on the photoelectric effect, Max Planck empirically derived a formula for that spectrum, and he assumed a hypothetically electrically charged oscillator in a cavity that contained black body radiation could only change its energy of minimal increment. He was not happy about this assumption. He was at his wit's end and could not make it work, his empirical formula work at all, until he did this mathematical, what he calls a trick, and he was kind of embarrassed about it. And what he did was he assumed that each, the energy had a minimal increment. Each was a chunk of energy. And then he did a statistical analysis using that that minimal energy increment. And it worked. It matched the measured values. He was able to calculate the proportionality constant for his equation from the experimental measurement, and that constant is named in his honor, and he got pretty close. So it was actually Planck who did that. Well, Einstein comes along in 1905 in his paper, and he explains what's going on. Back then, didn't believe that in the photoelectric effect that a wave of light would actually cause an electron to be emitted. Einstein's explanation for this observation was that light itself was quantized. Light itself is quantized, that the energy of light is not transferred continuously as in a wave, but only as small packets or quanta. The size of these packets of energy, which would later be named photons, was to be the same as Planck's energy element, giving the modern version of the Planck-Einstein equation, E equals hf. Einstein's postulate was later proven experimentally. The constant of proportionality between the frequency of incident light f and the kinetic energy of the photoelectrons or electrons was shown to be equal to Planck's constant. Einstein got the Nobel Prize for his suggestion that light was not a continuous wave, but small packets or quanta of energy. Okay, finally back to the particle model, and I showed this last time, where this is a picture showing a photon hitting a electron and having the electron being emitted. And the way I said it last time was that this is like the peak of the light of the particle model for light. Could be a G1 hitting a G1 or a cluster of G1s hitting this with enough energy to knock it out, knock a G1 particle out and emit a G1. That would be my understanding of the particle model's version of photoelectric effect. Summary: the G1s do not stop. Once they're moving at speed c or somewhere around that, they're going to continue to move all the way around, caused by the light in this case and caused by the battery in this case. Both of them adding G1s to the stream, to whatever's coming in, it's adding these G1s. And no matter what's coming into the battery, it's adding G1s back here. And the spreadsheet showed that there were 63,000 on each side, and hence of current of zero. They don't stop. Wave or particle, 1801, Young's double slit experiment indicated that light was a wave, and from there we have Maxwell's equations, and everyone saying, yes, light's a wave, light's a wave. In 1905, Einstein suggested that light was a particle, and because of that, we have the wave-particle duality paradox. Wave or particle or both or when or why or how. In 2015, I suggested that light was a stream of particles with a repetitive pattern. And I claim that there is no paradox. There's just particles with that repetitive pattern. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.